Welcome to Math 220. In today's video, I want to give you an overview of what this course is really about, and what I'm trying to do with this course, as much as possible. So broadly, I see the courses that we teach in this department as broken into three pieces. You can think of this as math being sort of broken into these three pieces if you like. So on the one hand, we have what's often called applied math. In the middle, we have what's called pure math. And then on the other hand, we have what's called statistics. And as I see it broadly, most of our courses fall in one of these three categories, although some of them are sort of a blend of them. But we have an intro course for each of these areas. And so the intro course for applied math is our course on ODEs, which is Math 351. Our intro course on statistics is Math 215. And this is intended to be our intro to pure mathematics. So the first goal of this course is really to get a sense of what is pure mathematics. And in so doing, we'll talk a little bit about sort of what these other sides are, but we want to get this idea of what is pure math, and additionally, how do pure mathematicians think? Now, I should be clear, I'm unambiguously a pure mathematician out of these three categories, but I would never do anything to disparage either of the other categories. I think all of these categories are great and interesting in their own way, as indeed all categories of human knowledge are interesting in their own way. So just as much as this is sort of like me breaking down math, there's all the sciences in their own area which also have their own overlaps with these various pieces, and so on. So I want to try and give at least a very, very short explanation of what I consider each of these areas to be. And then we'll sort of dive into talking at some length about what pure math is and some examples from history about what that is. So one way to think about these three kinds of mathematicians is to think about what motivates them. What makes a problem interesting to them? And so what motivates an applied mathematician is something that's connected to the physical world. So when I say math connected to the physical world, I'm including things like any sort of physics, so calculus of motion, all of that kind of thing, as well as things related to biology, these things related to things that you can touch. On the other hand, statistics is math related to analyzing data, where data is large quantities of information that have been collected about any sort of thing that you then have to synthesize into some meaningful conclusion. And so this might, for example, be the data that's collected from a scientific experiment, or it might be the data that's collected by what ads you click on Facebook, or it might be the data collected by pollsters who are trying to predict a presidential race. Any of these sorts of things connected to data, that falls under statistics. So what is pure math? Pure math is, in a sense, questions that are connected to the abstract mathematical world. And I'll give you a lot of examples of questions about the abstract mathematical world in a moment, but I just want to be clear, when I talk about the abstract mathematical world, I'm talking about sort of concepts unto themselves that aren't necessarily tied to anything physical. So when I say, for example, 2 plus 2 equals 4, there's no physical representation of 2 in the universe. 2 is an abstract concept, and so when we talk about 2 squared or 2 cubed, or the fact that 2 is even, or any of these sorts of facts, these are all very abstract things that are not being connected or motivated by the physical world. And so pure math is going to be really driven by raw logic. Indeed, ultimately, you're going to see one of the key ideas is this idea of a proof, which is going to be focused around the idea of knowing something with absolute certainty. Now, many mathematicians would tell you that, in a sense, only a mathematician can really know anything with absolute certainty. Whether that's true, whether you agree with that, whether by the end of this course you think a mathematician can even know something with absolute certainty, I'll leave that to you. I'll pause for a moment for you to appreciate this relevant comic that I think really captures the idea that a lot of mathematicians have when they think about the way that we interact with the abstract world. Now, one thing I want to stress is that though the names might suggest this, this distinction between these areas has nothing to do with usefulness. So, for example, next semester I'm teaching a course on number theory and cryptography, which is squarely in the pure math genre, because I'm not going to mention the physical world in it at all. But on the other hand, it's all about the applications of number theory to areas like cryptography, which are profoundly useful to human life. Modern human life, anyway. For example, every time you send a credit card number on Amazon and you have faith that no one will steal it, all of these things are based heavily on cryptography, which uses a great deal of number theory. On the other hand, there are a great many problems that are inspired by the physical world that are not necessarily in any way useful. So, for example, one of my colleagues at a previous institution studied the fluid dynamics on the moons of Jupiter, maybe not super useful to humanity to understand the fluid dynamics of the moons of Jupiter, but definitely applied because it's about understanding the physical world. So all of these areas have both sort of a theoretical side where you're interested in it for knowledge's sake, and then maybe some applications more related to it. So let's talk some more about examples of pure mathematics. So I'm now going to focus for a moment on number theory. Possibly I'm biased because I am a number theorist. And so what is number theory? Number theory is the study of the positive integers. So reminder, when I say integer, I'm talking about whole numbers. So we're talking here about 1, 2, 3, 4, 5, and so on. This infinite list. And so what sorts of properties am I talking about? Well, we're going to be talking about things like even numbers, and odd numbers, and prime numbers. And we'll talk about something called a perfect number in a bit. These are all properties that a positive integer might or might not have. Now, notice there are lots of numbers that you would think of as numbers like pi or 3/4 that are not integers, so they're not even part of this world. This world only consists of these numbers. Now, people have been studying number theory for a very long time. So some of the first published results in number theory go back to Euclid, who lived around 300 BC. But we have evidence that the Babylonians considered problems of number theory thousands of years before that. But Euclid's Elements is maybe the book that we have the most sense of what people knew. This is, again, around 300 BC. And I want to note, this is mostly a geometry textbook, but it also contains a few chapters on number theory. And one theorem that it contains is the fact that there are infinitely many prime numbers. So that is, if you start this list, 2, 3, 5, 7, 11, 13, 17, 19, 23, and you keep going, this list never ends. Reminder, prime numbers are numbers that are only divisible by themselves and 1. However, you might be noting isn't 1 on the list, but mathematicians explicitly exclude 1. So for me, a prime number is an integer strictly greater than 1 that is only divisible by itself and 1. I'll try and motivate at a later point why it is that mathematicians would prefer 1 not be a prime. But there are a lot of good reasons, even though it doesn't seem natural at first, why you would not want 1 to be prime. Now, I want to emphasize here that when I use the word theorem, when a mathematician talks about a theorem, they mean something that's been proven, something that's absolutely true in the sense of this XKCD comic that we saw earlier. And it might take a while for you to even think, how would you prove something like that there's an infinite number of primes? There is no amount of data you could possibly collect to convince you that this statement is true. I could give you a list of 1,000 primes, but that doesn't tell you that there's 1,001st prime. I could even give you a list of 10 billion primes, and it would still come nowhere close to showing you that there's infinitely many of them. So, in this course, we're going to do a lot of grappling with how would you actually prove something like this? And I promise, before the end of this course, we'll definitely talk about Euclid's proof that there are infinitely many primes. But Euclid was interested in a lot of other kinds of numbers too, other than just the primes. So Euclid was also interested in what the Greeks called perfect numbers. And so perfect numbers, like prime numbers, also involve the list of divisors that a number has. So if I look at the divisors of 6, then I get the set 1, 2, 3, 6. These are just the numbers that go into 6 with no remainder. If I look at the divisors of, say, 12, that'll work out to be 1, 2, 3, 4, 6, and 12. Now, the idea of a perfect number consists of doing something that's a little strange, that probably is not the first, second, third, or fifth thing that you would think to do. Namely, we're going to throw away the number itself, and then we're going to add the remaining divisors together. And so in the case of 6, if I do that, I get 1 plus 2 plus 3, which is 6. That's a little surprising. The sum of the divisors of 6, other than 6 itself, is 6. And this is what makes the number perfect. Whereas if I did this with 12, then I would get 1 plus 2 plus 3 plus 4 plus 6. And that would end up being 16, which is not 12. So 6 is perfect. 12 is not perfect. Now, this is definitely an idea that is not very intuitive. Probably you have no idea, like, how many perfect numbers there should be, or whether there should be more of them. I've shown you that 6 is perfect, but probably that's about the extent of your knowledge about perfect numbers at this point. I can probably convince you of a couple things. So, for example, I can probably convince you that no prime number is perfect. And the reason for that is that if you take a prime number, well, by definition, the divisors of that prime number are 1 and the prime itself. But then if you cross out the p and just add the remaining things, you would just get 1, which is not the same thing as p. Indeed, it turns out, just empirically, if you look through numbers and you go looking for perfect numbers are quite rare. So, for example, if you look through all the numbers up to 100, there are only 2. Well, one of them is 6. You might ask me what the other one is, and I will happily tell you. The next perfect number is 28. If I write down the divisors of 28, that will be 1, 2, 4, 7, 14, and 28. I'm going to throw out the 28. And then you can check my claim, because if you take 14 plus 7, that'll be 21, plus 4, that'll be 25, plus 2, that'll be 27, plus 1, that is 28. So 28 is perfect. Just to give you a picture of how rare these numbers are, I'm going to show you a list of the first 8 perfect numbers. You'll notice, already by the 8th one, this number is absurdly large. Probably larger than any number you would likely consider in any realistic circumstance. But the Greeks were absolutely fascinated with these numbers. And indeed, because of this group called the Pythagoreans, which were sort of a math cult, if you can believe this, they attributed a great deal of mystical significance to numbers. And of course, having named numbers perfect, they attributed a great deal of significance to these. Now, I'll note Euclid was also interested in these. And indeed, Euclid listed the first 4 of these. So Euclid knew that 8,128 was perfect. The next number on the list would not be found for a great number of centuries afterwards. But Euclid actually found a machine for producing these perfect numbers. Namely, Euclid proved the following theorem. Namely, he proved that if 2 to the n minus 1 happens to be prime, and I'll point out, there's no reason to suspect that this number will happen to be prime, but if it does happen to be prime, then this number, which is 2 to the n minus 1 times 2 to the n minus 1, written both ways that you could interpret that, this number is always a perfect number. So, Euclid's theorem here is an if-then statement, and we're going to talk a lot about if-then statements in the course, but it starts with if 2 to the n minus 1 is prime. So, what I should come up with is a list of n's where that's true. If I tried n being 1 here, that would be 1. Remember, 1 is not prime to a mathematician. 2 squared minus 1, that would be 3. That's prime, yep. 2 cubed minus 1, that would be 7. That's prime, great. 2 to the 4th minus 1, that would be 15. No good. 2 to the 5th minus 1, that would be 31. That's prime. 2 to the 6th minus 1, that would be 63. That's not prime. It's divisible by 3. 2 to the 7th minus 1, that'll be 127. Now we might be a bit past your ability to determine if this is prime on your own, but this in fact is prime. So this was the first part of Euclid's statement, if 2 to the n minus 1 is prime. So in these 4 cases that we found so far, we get the following nugget of information. Namely, we get that 2 to the n minus 1 times 2 to the n minus 1 is perfect. So I want to carry that out for you. So if n is 2, then we get, following this formula, 2 to the 1 times 2 squared minus 1. Okay, that is 6. That was the first perfect number I showed you. If n is 3, then you get 2 squared times 2 cubed minus 1, which is 4 times 7, which is 28. That's the second one I showed you. Next, following along, you could try n is 4. This will give me 2 cubed times 15, which is 8 times 15, which is 120. But notice here when n is 4, we did not meet the condition. Namely, 2 to the n minus 1, it's not prime. And so, you might expect it's not going to work here if I try and list out the divisors of 120. Indeed, if I start listing out the divisors of 120, well, let's start at the top. So 60, 40, 30, and actually there's lots more, but if you're paying attention, I've already written down 3 that add to 130, so this is definitely not a perfect number. So again, this being an if-then statement means that, again, only if the if part works do we get the then part. If we go ahead and write down n is 5. That will go ahead and give us 496. And if we go ahead and write down n is 7, that'll give us 8,128. So we see how it is that Euclid knew these 4 perfect numbers, because Euclid knew this theorem that he had proven. And as soon as you know this theorem, even if you don't have a calculator, it's not so bad to find this many prime numbers in this list, and those automatically spit out perfect numbers for you. Now, if you keep going on this table, you have a long string of misses. 2 to the 8th minus 1 is not prime, 2 to the 9th minus 1 is not prime, 2 to the 10th minus 1 is not prime, 2 to the 11th minus 1 is not prime, 2 to the 12th minus 1 is not prime. The next one you find, where this if 2 to the n minus 1 is prime, where that actually checks out, the next one is 13, where 2 to the 13th minus 1 is 8,191, which is prime. Now, I'll go ahead and note this number, or the fact that this number was prime, was not found, at least as far as we know, until 1,500 years after Euclid. So it was a good deal later before someone bothered to go this far down to try and find this next prime number in this list. But, just like Euclid's theorem would tell you, if you take then the number 2 to the 13th minus 1 times 2 to the 12th, then you get the number 33,550,336. And I will leave it to you to check that this number is perfect. So a natural question to ask about all of this is, why? Why 2,300 years ago did Euclid think about these things? And there really is no answer beyond the fact that he and those around him found this stuff interesting and beautiful in its own way. And at its heart, that idea of something being interesting and beautiful on its own lies at the heart of how a lot of pure mathematicians think about mathematics. If you're a curious sort, you might have some follow-up questions about the story I've told you so far about Euclid and perfect numbers. So, one question you might ask is, how many perfect numbers are there? And the answer to this is, well, we know a total of 51. The largest of those we know has about 50 million digits. Take a moment to just think about how preposterously large a 50 million digit number is. So this is a number that's on the order of 10 to the 50 million. So that is astronomically larger than any number you would ever consider in any physical context. It is much larger, for example, than the number of atoms in the known universe, which, just for sake of comparison, physicists think is somewhere about 10 to the 80th. So this number dwarfs that by a ridiculous margin. But there's no reason to expect that we have all of the perfect numbers. In fact, everyone believes, basically, that there should be infinitely many perfect numbers, just like there were infinitely many prime numbers. But no one can prove it. And so this is what mathematicians would call a conjecture. So by conjecture, I mean this is a precise statement. It says something very specific, and we have evidence to suggest that this statement is true. But none of that amounts to saying that we've proven that this is true. It could be false. It could be that there are exactly 86 perfect numbers, and that after we find the 86th one, we'll never find another one again. It's not what people believe, but it's possible, for all we know. So a conjecture is something that generally a wide number of people believe, but can't prove. So basically the word conjecture in layman's terms means guess. Usually in math, when someone calls something a conjecture, they mean a little more than guess, but significantly less than theorem. Here's a second question that might come up. If I pull back up this list of perfect numbers that we know, And indeed, even if I showed you the list of all 51 perfect numbers that we know, you might notice that all of them are even. So all perfect numbers that we know are even. Now, I'll go ahead and note any perfect number that Euclid's formula gives you is definitely going to be even, because you're going to get it always by multiplying a huge power of 2 by something, and if you multiply a huge power of 2 by something, it's always going to be even. But nevertheless, that doesn't actually answer the question of whether there could be odd perfect numbers. Now, seemingly the Greeks took this for granted, because they believed that odd numbers were in some sense defective, so they believed it was just obvious as a matter of understanding the universe that odd numbers couldn't be perfect. At least the Pythagoreans seem to have believed this. But no one ever really wrote down a proof of this. In fact, this is still an open question. So, what does being an open question mean? It means no one knows the answer. So what do we know? Well, we at least know that if there is an odd perfect number, it has to be pretty big. And when I say pretty big, I mean that it has to be at least bigger than 10 to the 1500th. Now, again, this is a preposterously large number, not perhaps by comparison to this large perfect number that we talked about earlier, but this number has to be astronomically large if there's an odd perfect number. And it has to satisfy a long list of conditions that mathematicians have proven. And so, basically, if you're curious, how do you get a statement like this? How do you know that this is true? In order to get a statement like this, you have to prove a bunch of theorems about if there is an odd perfect number, then it has to have this property and this property and this property. And then once you have that list of properties, you have to check all the candidates by computer to see if any of them actually have this property. And then when you see that they don't, you get a statement like this. Please note, 10 to the 1500th is way too large to just write yourself a for loop that's like, for n from 1 to 10 to the 1500th, check if it's perfect. That program will not finish and will not get you to anywhere near this. But through a combination of clever math and clever computer science, people were able to get this result. But as far as anyone knows, you check a little bit further than this, maybe you start finding some odd perfect numbers. Who knows? So, third question. It's also pretty natural to ask. Euclid gave us this formula that let us find the first handful of perfect numbers. Okay, we showed before that this formula, in fact, gave you at least the first 4 perfect numbers. In fact, it also gives you at least the first 5 perfect numbers, because this is the next one. But Euclid never did anything to promise that this was the only kind of perfect number that you would find. Now, certainly if you find an odd perfect number, it's not of this form. But you might ask, are there any other even perfect numbers? That is, are there any extraneous even perfect numbers not yet captured by this? Basically, this is asking, does every even perfect number come from a prime that looks like this? And this question, we actually do have an answer to. And the answer is actually yes. And so the answer here is a theorem due not to Euclid, but to Euler. Please note that though Euclid and Euler have similar names, they lived quite a bit apart, as Euler lived in the 1700s. But Euler, in fact, proved every even perfect number has the form of Euclid's theorem. So this is a pretty complete answer, at least to the story about even perfect numbers. But still, getting to this answer, where Euclid says, hey, if you start with a prime that looks like this, you get a perfect number. And Euler says, hey, if you start with an even perfect number, it came from Euclid's formula. This was a 2,000-year saga. Euclid and Euler did their work 2,000 years apart. And even if you consider the story pretty much done, it's still not completely done, because we still have the question about how many primes there are of this form. Now, for reasons that are not super easy to understand historically, these primes are called Mersenne primes. So just to be clear, when I talk about Mersenne primes, we're talking about the ones that are 1 less than a power of 2. So 3, 7, 31, 127, those are the first 4. Note this is kind of unfair because Mersenne lived 1800 years after Euclid, and Euclid talked plenty about these prime numbers. But whatever. History often misnames things. But these numbers actually turn out, rather interestingly, to be important to cryptography. Indeed, it's somewhat of a pleasant coincidence that for 2,000 years, people thought about all of these questions about number theory and did all of this work for no reason other than, hey, this stuff is pretty and interesting and I want to know the answer to these questions. Indeed, there's just something very human about the fact that it's just annoying that we don't know whether there's an odd perfect number or not. It seems like we should know that. But we don't. But this desire led people to discover all of this mathematics for no reason other than that it was neat. And then, in the 1900s, computers happened. And number theory turns out to be the basis of a lot of modern computing. So the fact that mathematicians for millennia thought about these things turned out ultimately to play very well into the narrative of human history. So, what are our goals for this course? Well, our first goal is to understand this idea of mathematical proof, and to be able to produce our own proofs. Our second goal is to understand the mathematical mindset, and in particular, what mathematicians mean when they talk about truth and beauty. Next, I want to give you some sense of the idea of what modern mathematical culture looks like, and what the history of math looks like. And finally, I'm going to end the course with an overview of the structure of modern mathematics. And by that I mean, when you see an upper division math course called combinatorics or complex analysis or any of these sorts of things, you might not have any idea what those words mean, and I want to give you some sense of what those areas are and what they're concerned about and what kinds of things mathematicians in those areas are interested in to help you choose which courses you might want to take as you go through your time here at Luther. So, roughly speaking, we're going to talk about in this course, first, we're going to develop an understanding of mathematical language and logic. So before we can prove things are true or show things are false, we need to understand what the things that are true and false are, and what the operations we can take to put those pieces together are. Next, we'll talk about methods and structures of proof. So every proof is different, but there are a lot of common themes that you'll see over and over again throughout mathematical proofs. So I'll give you a lot of examples of historically important proofs, and we'll also produce some of our own. Next, we'll talk about sets and functions, which are as close to universal an object in mathematics as possible. Every area of mathematics cares about sets and functions. And so we'll talk about those, and we'll talk about the weird thing that mathematicians mean by functions, which is slightly different than the thing that you learned about in calculus. We'll talk with some precision about sets. And basically the idea of these first 3 points in this outline, once you understand these 3 things, you should be very well versed and prepared to do all the things in math that you can do here. You'll be ready to write a senior thesis and all of these kinds of things. But we've got to have some fun. So after that, we're going to put all of these tools together to talk about the subject of sizes of infinity. So that is, we're going to talk about this idea that you may have heard about before, that some infinities are larger than others. And that's a very abstract idea that's maybe hard to put into concrete terms, but we're going to use the abstract structure in logic, as well as the proof methods that we've talked about together with functions and sets, to be able to say coherent things about what exactly we mean when we talk about infinity and talk about some infinities being larger than others. Sprinkled throughout the course, we'll have little detours where we'll talk about mathematical culture. We'll learn a little neat thing about a small area of math. We'll read some articles written by mathematicians or about mathematicians that go over some aspects of math culture. And so by the end of this course, I hope that you have a much better understanding of what mathematicians mean when we talk about math. I'm going to leave my introduction there. In the next video, we're going to begin our discussion of mathematical language and logic, and we're going to start trying to put those pieces together. But that's all for now. I'll see you next time.